In this lesson, we will be deriving the unit circle. So this is so important. This lesson is really important. And we will also be defining our 6 trigonometric functions as circular functions. Now, so far in our class, we have defined the 6 trig functions so that the domain of our trig functions, of each function, is a set of angles. And we've already defined these angles to be in standard position. Remember, that means the vertex of the angle is at the origin and its initial side is on the positive x-axis. And these angles can be measured in degrees or in radians. So that's what we've talked about so far. That's how the 6 trig functions are defined. In advanced courses of mathematics, like calculus, for example, it's necessary for the domains of our trig functions to consist of real numbers rather than angles. So we need to modify our domains. We need to change the domains of our six trig functions. And we're going to do that by drawing on the relationship between an angle, let's call the angle theta, and an arc on a circle. Usually the arc that is intercepted by your angle theta has length. The arc has length s. We use the letter s to represent the length of the arc on the circle. All right, so let's do it. Let's start to derive our 6 trig functions as circular functions. All right, this is going to change the domain like we had just said. So what I am starting to draw here is the unit circle. We know that from earlier studies in algebra, the unit circle is a circle whose radius is 1. Right, so the radius is 1, and that's why we call it the unit circle. And we're going to conveniently place the center of our circle. We're going to superimpose it onto the rectangular coordinate system and place the center of our circle right at the origin of the Cartesian plane. So the unit circle is the circle whose radius is 1 and whose center is 0, 0, the origin. The equation that defines the unit circle is x squared plus y squared is equal to 1. You'll recognize, hopefully, this equation from earlier studies in algebra when you were studying your conics. All right, so this is the unit circle. This is the point 1, 0 on the unit circle, 0, 1, negative 1, 0, and 0, negative 1. Those are very important points. So what we're going to do is we're going to start out right here at this point 1, 0, and we're going to measure an arc. And we're going to call this arc, we're going to say that the length of this arc, here's the arc, I'm highlighting it in yellow. We're going to say this arc here, let's just say it's heading in that direction and that much. And we're going to say the length of that arc is s. Now I drew an arrow here showing you the direction in which it's opening. If s, which is the arc length of the length of the arc, if s is positive, then the arc is opening or measured in a counterclockwise direction, like this one. If s happens to be negative, then the arc will open or measured in a clockwise direction. Okay? If s is exactly 0, if the length of the arc is 0, then no arc is measured at all. Okay, I want to let the end point of this arc right here, this is the end point, right, be the point x comma y. Let's label that. So there we have our point, and we can see that the angle that we're going to call theta that intercepts this arc is here. If I can draw it for you now, this is the angle, let's call it theta, that intercepts our arc of length s. Okay, and then don't forget that this is what we're going to call r, right? From the center to this point, this is the radius of the circle, the radius here, which is just 1. Here's our angle theta measured in radians, and this is the arc of length s that is intercepted by this central angle. All right, so we have learned from earlier studies that the arc length s is equal to the product of the radius of the circle and the radian measure of angle theta. This is from earlier lessons. Now, When the radius has measure 1 unit, then this just becomes 1 times theta. That is to say, s is equal to theta. So the 6 trigonometric functions of angle theta then, found in radians, by choosing a point x comma y on the unit circle, can be rewritten as functions of the arc length s. So instead of having sine of theta, tangent of theta, cosine of theta, we're going to say sine of s, cosine of s, tangent of s, and so forth. S is a real number, okay? So when the 6 trigonometric functions are defined this way in terms of s, of arc length s, then we call them the circular functions. So that's why they're called circular functions whenever you interpret the 6 trig functions in terms of arc length s. So let's write this down. All right, so here's our first one. Sine of s, and s is a real number represented by the directed arc on the circle, okay, on the unit circle. Sine of s, we used to say sine of theta, but now theta is equal to s, so we're saying sine of s. Now, we defined in earlier studies, we defined sine of theta to be y over r, y over r. But notice that r, the radius of the circle, is just 1. So y over r becomes y over 1, which is just y. So sine of s is equal to y. Cosine of s is x over r. Remember x over r from earlier studies from chapter 1 of our textbook? But again, x over r would just become x because r is 1. Tangent of s is defined to be y over x. Here we have to be very careful. We cannot have x to be 0 here, because if x is equal to 0, then tangent of s would be undefined. Okay, so be careful. The next 3 are just reciprocals of what we have just written. So we have cosecant of s is just 1 over y. Secant of s is 1 over x. It's the reciprocal of what we've already written. Cotangent of s is x over y. We have to be careful with this one. Cosecant would be undefined. Cosecant of s would be undefined if y is 0. Secant of s would be undefined if x is 0. Cotangent of s will be undefined whenever y is 0. Again, so these are our circular functions, which are our trig functions, right? The same trig functions we've been talking about, but now they're all defined as in terms of s, which is a real number that is represented by this arc length here. Okay, so now the domain of our 6 trig functions consists of real numbers. Now, before we move on, I want to draw the connection here. Y is sine of s, and x is cosine of s. So when you come over here to this point, which has coordinates x comma y, we can now rewrite these coordinates as cosine of s comma sine of s. Remember, x represents cosine of s. It's right here. So replace x with cosine of s and replace y with sine of s. So this is very important, and this leads us to the unit circle with all of our special angles and quadrantal angles with function values as well. I'll show you that on the next slide. But what I want to really drive home for you here is S is the arc of length. This is arc length here that is related to the angle theta in radians that intercepts that arc, right? And the first coordinate here for this point, and this point is the intersection of the terminal side of our angle and the unit circle. That's what this point is. This point is on the unit circle, and it is the point at which the terminal side here of this angle intersects the circle. And the first coordinate x is cosine of s, and y is sine of S. All right, so look at this. So I have the unit circle started here. I'm not done, but notice that the radius is 1. The center of the circle is at the origin of our plane. And we have these points 1, 0, 0, 1, negative 1, 0, and 0, negative 1. The first angle I'm going to look at here, 30 degrees, which is the same as pi over 6. This would be the arc right here on the unit circle that is intercepted for this angle, pi over 6 and 30 degrees, or intercepted by this angle. Okay, so this would be S, the arc of length S here. Now this point right here on the unit circle has coordinates x, comma, y, x, comma, y. But remember, x, the first coordinate, is equal to cosine of s. It's equal to cosine of this arc length s, which corresponds to this angle, pi over 6, or 30 degrees. So x here is cosine of pi over 6, cosine of 30 degrees, which is root 3 over 2. The y-coordinate is sine of s, that is to say, sine of pi over 6, or 30 degrees, which is 1/2. So these coordinates here, these are real numbers, these are function values for sine of 30 degrees, cosine of 30 degrees, and sine of 30 degrees. Or if you prefer radians, cosine of pi over 6 and sine of pi over 6. The next one would be a 45 degree angle, or pi over 4. The arc would be from here all the way there. This would be all of the arc of length S here. And this is the arc that would be intercepted by this angle here. And the coordinates for that point on the unit circle, of course, would be x, comma, y. But x is defined in our definition as cosine of s, which is cosine of pi over 4. So it'll be root 2 over 2. The y-coordinate is defined to be sine of s, sine of pi over 4, or sine of 45 degrees, which is root 2 over 2. Our next special angle is 60 degrees, or pi over 3, and this would be the arc that is intercepted on the unit circle by this angle here, and the point here on the unit circle, of course, has coordinates x, comma, y, but the x coordinate is cosine of s, which in this case is cosine of pi over 3, which we know is the same as cosine of 60 degrees, which is 1/2. And sine of 60 degrees is root 3 over 2. I could get at that. Okay, there we go. Root 3 over 2. All right, very good. Now, let's not forget that this angle here is 0 degrees, which is 0 pi, 0 radians. And the coordinates are 1, 0. 1 is cosine of 0 degrees, and 0 is sine of 0 degrees. So there we have it, 0 degrees or 0 radians. So this first coordinate, which is x, of course, 1 represents cosine of 0 radians, or cosine of 0 degrees. 0 represents sine of 0 radians, or sine of 0 degrees. Similarly, this point 0, 1, 0 represents cosine of 90 degrees, or cosine of pi over 2, and 1 represents sine of 90 degrees, or sine of pi over 2. The rest of the function values all around the unit circle will be mirrored images of all of these function values here. For a circle, for the unit circle, you have symmetry with respect to the y-axis, you have symmetry with respect to the x-axis, and you have symmetry with respect to the origin. So here is all of quadrant 2 of the unit circle. all of our special angles and their degree measure and radian measure, along with all of their function values. Now, I want you to notice that all of these function values here are the mirrored image of these ones here across the y-axis. So when you have the mirrored image, for example, of this point across the y-axis like this, the y-coordinate stays the same. Look at 1/2, 1/2. The only thing that changes is the x-coordinate. It's the opposite thereof. So instead of positive root 3 over 2, it's negative root 3 over 2. And that's true for all these points. Look at the x-coordinate changes to its opposite, positive root 2 over 2 to negative root 2 over 2, while the y-coordinate stays the same. And the same is true for each point. That's because of symmetry across the y-axis. So next I'll get quadrant 3 here by reflecting these function values. I always go back to quadrant 1 across the origin, symmetry with respect to the origin. So when you move down to quadrant 3, notice that both x and y values are negative. All of these function values here will be the same, except both x and y will be negative. So here's quadrant 3 with all of our special angles, both in radian measure and degree measure. And the function values that I'm about to put here for each one of these angles, for each point that's on the unit circle, will correspond to these function values here, but the only difference is all of the coordinates will be negative. So here we have it. So it is very important that you understand that as long as you know these coordinates in quadrant 1, you can get the mirrored image of those with respect to the origin for quadrant 3. Or you can get the mirrored image with respect to the y-axis to get quadrant 2. So just really focus on quadrant 1. All right, to wrap it up, this is quadrant 4. And notice that all of these function values here are the same as these, but they've been reflected across the x-axis. So what happens when you reflect a point across the x-axis, the x values stay the same. Notice the x values stay the same. The y values turn into the opposite. Okay, so this is symmetry with respect to the x-axis. This is the unit circle in all of its glory. Okay, so you have every special angle, every quadrantal angle, both in degree measure and radian measure, and you have the function values on the outside. Okay, this is what you need to know extremely well. But please focus on quadrant 1. Spend your energy remembering quadrant 1 because you can use symmetry to get all the rest. Now, to start leading up to the domains of our trig functions, remember that cosine of s is defined to be x and sine of s is defined to be y. This is the equation for the unit circle, so it's an identity. And we can substitute here. We can substitute cosine of s for x and sine of s for y. And with that substitution, we would have cosine squared of s plus sine squared of s is equal to 1. And this is the Pythagorean identity. We already have this in our notes from earlier, but here it is again. All right, so think about this. The ordered pair x comma y represents a point on the unit circle, right? And therefore, because it's on the unit circle, we know that x must be less than or equal to 1, but greater than or equal to -1, because you're on the unit circle. In other words, the largest that x can be is 1. That's the largest it can be. The smallest it can be is -1. If I go back up to the unit circle here and show you the unit circle, here it is. Here, please look at your x-axis. Your x-axis goes from -1 to +1, and that's why I'm saying the x values must be between -1 and +1. These are all of your possibilities for x. X is between -1 and 1. And notice the same thing is true for your y values. Y also must be between -1 and 1. So for this conversation here, I have x must be between -1 and 1, and the same thing is true for y. All right, very good. Okay, now that must mean, if you substitute, that cosine of s must be between -1 and 1, and sine of s must be between -1 and 1, right? Because x is what cosine of s is, and y is what sine of s is. Now, what's really interesting here is no matter what you plug in for s, both cosine of s and sine of s exist. They're both defined for whatever you plug in for s. So the domain of these functions is a set of all real numbers, because no matter what you plug in for s, sine of s and cosine of s exist. Now, that is not true for tangent of s and also secant of s. Please notice that both of these functions have something in common. They're both defined with x in the denominator. So both of these functions, each one of them, will be undefined whenever x is 0. So when is x 0? Well, let me list out some values for which x will be 0. If s is equal to pi over 2, then x would be 0. Here, let me show it to you on the unit circle. Let me scroll back up. Oops, sorry. Let me scroll back up to the unit circle. Look at pi over 2, please. Look at pi over 2. What is your x value? Your x value at pi over 2 is 0. So when s is pi over 2, x is 0. Look at this. When s is 3 pi over 2, x is 0 again. So when I come over here, back, if I can scroll back here, I'm talking about tangent and secant. These will be undefined if s is pi over 2, or if it's 3 pi over 2, or if you keep going around the unit circle, 5 pi over 2, or 7 pi over 2. The same will be true for like negative pi over 2, negative 3 pi over 2. If you look at all of these angles, you'll notice, you will notice that the x value is 0. So what all of these have in common, all of these s values have in common, these are all odd multiples of pi over 2. Odd multiples of pi over 2. This is 1 pi over 2, 3 pi over 2, 5 pi, 7 pi over 2, negative 1 pi over 2, negative 3 pi over 2. All of these are odd multiples of pi over 2. So basically, I can sum it all up at like this. If s is 2n plus 1 pi over 2, this is our way of saying odd multiples of pi over 2. If s is any one of these values, then tangent and secant will be undefined. Okay, so actually, let me actually do this. S must not be equal to this. S must not be equal to any odd multiple of pi over 2, or else tangent and secant will be undefined. Hey, here n is an integer. Let me write that. For n being an integer. Actually, it's written better that way, where n is any integer. So watch this. Plug in the integer 0. 2 times 0 is 0, and 0 plus 1 is 1. 1 times pi over 2 is pi over 2. So when you plugged in 0, you generated this odd multiple of pi over 2, the first one. If you let n be 1, 2 times 1 is 2, and 2 plus 1 is 3. 3 times pi over 2 is 3 pi over 2. So if you let n be 1, it generates this odd multiple of pi over 2. If you let n be 2, 2 times 2 is 4, 4 plus 1 is 5, 5 times pi over 2 is 5 pi over 2. So this expression is generating all of your odd multiples of pi over 2. So tangent and secant will be undefined for any odd multiple of pi over 2. Okay? The last two functions, cotangent of s and cosecant of s, have something in common. They're both defined with y in the denominator, which means that both of them will be undefined whenever y is 0. Now think about whenever y is 0. Y would be 0 if s were 0 pi, 1 pi, 2 pi, 3 pi, etc. Negative pi, negative 2 pi, negative 3 pi, etc. Let me prove it to you. I'm going to show you on the unit circle each one of these angles, and I'm going to show you that at each one of these angles, y is 0. So come with me to the unit circle, which is back up here, if you don't mind me scrolling here. All right, I hope I'm not making you dizzy. All right, here we go. Look at 0 pi, which is right, right here, 0 pi. Look at your y value. It's 0. Go with me to pi. Look at your y value. It's 0. Go with me to 2 pi. Your y value is 0. Go with me to 3 pi. Your y value is 0. Go with me to 4 pi. Your y value is 0. And the same is true with negative pi. Your y value is 0. Negative 2 pi. Your y value is 0. So at each one of these s values, I'm sorry if I'm making you dizzy here, at each one of these s values, your y value is 0, which means cotangent and cosecant would be undefined. Now, these are all of the multiples of pi. These are multiples of pi. So what we're saying is cotangent and cosecant will be undefined at any multiple of pi. In other words, s must not be equal to any multiple of pi. And this is how we write any multiple of pi, okay? Again, where n is any integer, okay? Where n is any integer, okay? This is how we generate every single multiple of pi. Let n be 0, you would have 0 pi. Let n be 1, you would have 1 pi. Let n be 2, you'd have 2 pi, and so forth. So in conclusion here, the domains of the circular functions sine and cosine, the domain is all real numbers. Okay. The domain for tangent and secant is the set of, I can do that better, the set of all s such that s is not an odd multiple of pi over 2. This is called set builder notation. Okay, let's see. For cotangent and cosecant, it is the set of all s such that s is not any multiple of pi. Okay, these are the domains of all of our trig functions or circular functions. What I want to show you last here before we look at a few examples and then call it a day, I want to show you how we find values of circular functions. Now here I have the unit circle, x squared plus y squared is equal to 1. I have shown you an angle theta here, which is a central angle, and it's intercepting an arc here of length s. Remember, s is, here I can write it really quickly for us. S, and we wrote this down earlier, is equal to the product of the radius of the circle and theta. But again, remember that the radius is 1 because this is the unit circle. So it's really, s is exactly equal to theta. And that's why I wrote it right here. S is exactly equal to theta. Now what I want us to do is something that we have done in the past, and that is to draw the perpendicular from this point where the terminal side of this angle theta intercepts the unit circle, this point right here. Draw the perpendicular down to the x-axis. All right, we've done this before. When you drop the perpendicular down to the x-axis, this vertical distance here is y. This horizontal distance here is x. Just from here, the origin to where the perpendicular meets the x-axis, just this distance right here is x. Vertical distance is y. This distance here is r, which is the radius of the circle, which is equal to 1. All right, now this point here on the unit circle has coordinates x comma y. So these are the x and y coordinates for this point right here. Let me actually point to it. So right there. Okay, but don't forget that x is defined to be cosine of s and y is defined to be sine of s. So the length of the arc s, okay, the length of the intercepted arc is the real number that corresponds to the radian measure of angle theta. Okay, the length of the arc is the real number that corresponds to the radian measure of angle theta. Okay, so let's look at some examples so we can put all of this information to work. Okay guys, find the exact values of sine of negative 3 pi, cosine of negative 3 pi, and cotangent of negative 3 pi. Now, evaluating a circular function at the real number negative 3 pi is equivalent to evaluating it at negative 3 pi radians. So let's first see a picture of where is negative 3 pi radians. Where is that on the unit circle? So allow me to draw this for you. Negative angle measure means clockwise direction. So this is negative pi, negative 2 pi, negative 3 pi. This much is negative 3 pi. And on the unit circle, do you remember what the coordinates are for this point right here on the unit circle? The coordinates are negative 1 and 0. This value here is x and this value is y, right? That's the ordered pair, x comma y. X represents cosine of s and the y coordinate represents sine of s, right? And the s value we're considering at the moment is negative 3 pi. So therefore, sine of negative 3 pi is equal to 0. Cosine of negative 3 pi is equal to negative 1. Let me write that down. Sine of negative 3 pi is equal to 0. Cosine of negative 3 pi is equal to negative 1. To find cotangent, we can use a quotient identity. Cotangent of negative 3 pi, if you'd like, is equivalent to cosine of negative 3 pi divided by sine of negative 3 pi, which would be equal to negative 1 over 0. So cotangent of negative 3 pi would be undefined. Okay? Whenever an angle is quadrantal lying on the x-axis, cotangent is always undefined. All right, find each function value, sine of 4 pi over 3 and cosine of 4 pi over 3. I am reminding you of the unit circle and where 4 pi over 3 is. If you want to look at your unit circle, you can, but you're going to see that 4 pi over 3 is about right here. And if you look at your unit circle, you'll find that the coordinates here are negative 1/2 and negative root 3 over 2. Go ahead and look at your unit circle and confirm that these are the coordinates for this point here that lies on the unit circle. Okay, everybody, this value here, the second coordinate, is sine the sine value of 4 pi over 3. This first coordinate is the cosine value of 4 pi over 3. So the unit circle just gives it to us as long as we understand this is sine of 4 pi over 3. Sine of 4 pi over 3 is equal to negative root 3 over 2. Okay, that's the answer, right? That's this value right there, okay? And then cosine of 4 pi over 3 is negative 1/2. That is this number there. Okay, everybody? The next one they ask us for is tangent of negative 9 pi over 4. Let's move around the unit circle, okay? Now we're going to have to move in a clockwise direction because this angle is negative, okay? And so what we're going to do is we're going to move, here we go, clockwise. This much is negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4, negative 6 pi over 4, negative 7 pi over 4, negative 8 pi over 4, negative 9 pi over 4. Here it is right here, folks. Okay, and so the angle is something like that right there. There's negative pi over 4, hitting the unit circle right there. Now, if you look at the unit circle, this is the same location as 7 pi over 4. Look at your unit circle. And the coordinates there at 7 pi over 4, you can confirm, but it is root 2 over 2 and negative root 2 over 2. So then what we can write is, watch this, tangent of negative 9 pi over 4 will be equivalent to tangent of 7 pi over 4, right? And remember that tangent is defined to be y over x. Well, ladies and gentlemen, this is your y value right here, and this is your x value. So then tangent of 7 pi over 4, which is the same thing as tangent of negative 9 pi over 4, is equal to negative root 2 over 2, that's your y value, over positive root 2 over 2. So the final answer is negative 1. All right, let's do this one. Sine of 11 pi over 6. What I'm going to do here is I am going to convert. I'm trying to show you different ways to find these function values. I'm going to convert 11 pi over 6, which is in radians, to degrees. Now, we talked about how to convert from radian measure to degree measure. So here you would multiply 11 pi over 6 by 180 degrees over pi. Okay, if you do this, you will find that 11 pi over 6 is equivalent to 330 degrees. Now, this is quadrant 4. So we already know our final answer will be negative because we're in quadrant 4 and speaking about sine. Your reference angle here is 30 degrees. So sine of 330 degrees will be equal to the opposite of sine of 30 degrees. The negative sign is here because we're in quadrant 4 and our answer should be negative. 330 degrees is in quadrant 4, so we just subtract 330 from 360 to get 30 degrees. And so our final answer will be, because we know the quadrant 1 so well, sine of 30 degrees is 1/2, so the final answer is just negative 1/2. So this approach was using a reference angle and converting radian measure to degree measure if you feel more comfortable with degree measure. Our next example asks us to find a calculator approximation for sine of 3.42. Now, please do not misunderstand this. 3.42 is in radians. We know that because there's no degree measure, so this must be understood to be in radians. Because of that, please double check your calculator. Make sure it's in radian mode. Okay, so when you punch this into the calculator, you should get approximately negative 0.2748. Of course it's negative because this radian measure, 3.42, you and I should know that this is quadrant number, what is it? 3. That's right, quadrant 3. We know this is in quadrant 3 because 3.42 radians is a little bit greater than pi, so it must be in quadrant 3, and in quadrant 3 sign is negative. The next one is secant of 5.6041. Now this is in quadrant number, do you know? Quadrant number 4, that's right, quadrant 4. And in quadrant 4, secant is positive, so I know my final answer will be positive. Now, in order to find this function value, what you may want to do is use the reciprocal identity. Secant of 5.6041 will be equivalent to 1 over cosine of 5.6041. Okay, you should get approximately equal to 1.2851. All right, this will be the last example for the lesson. Find each value as specified. Approximate the value of s in the interval 0 to pi over 2. So this is quadrant 1. Let me write that here. This is quadrant 1. If sine of s is equal to 0.3210. Now I want to be very clear. They gave us the function value. We have to find the real number that corresponds to this sine function value, okay? Whenever we did this in the past, we would always use an inverse sine function, okay? So we would say s is equal to inverse sine of 0.3210, okay? Whenever they give us the output and then ask us for the input, we have to use an inverse function, okay? All right, so then this will be equal to, s will be approximately equal to 0.3268. Cool, let's do another one. All right, so here, this is the last part. Find the exact value of s, the exact value, so we do not want to use a calculator. Find the exact value of s in this interval 3 pi over 2 to 2 pi. Please notice that this is quadrant number 4. And they tell us tangent of s is negative root 3 over 3. All right, so the first thing I want you to notice is that the absolute value of tangent of s, we did something similar to this before, is equal to the absolute value of negative root 3 over 3, which of course is positive root 3 over 3. Now, because I know that s prime, right, or the reference arc, I'm not going to say reference angle, but the reference arc will be in radians, right? We know we want radians and not degrees because look at the interval. They did not say 270 degrees to 360 degrees. They're using radians, so let's stay in radians. Because of this output and this function, I know that the reference arc must be pi over 6. Pi over 6. If the reference arc is pi over 6, that must mean, here's the picture for us. Here's the reference, pi over 6. But if we are in quadrant 4, then you just get the mirrored image, which would be right here. You don't want to say negative pi over 6. You're going to want to say 11 pi over 6. Let me show you. You have to go all the way around like that. Okay? Actually, from the x-axis, really. all the way around. This is 11 pi over 6. Okay, so then the answer is S must be exactly 11 pi over 6. 11 pi over 6 is the reference, 11 pi over 6 would be the angle in quadrant 4 whose reference angle is pi over 6. Be careful, you don't want to say negative 11, negative pi over 6. Negative pi over 6, by the way, negative pi over 6 would be right here, everybody. Negative pi over 6. Opening clockwise, that's negative pi over 6. You don't want to say negative pi over 6 because it's not inside this interval, right? So we want to make sure that the angle we give is inside of this interval. All right, we've come to the end of this lesson. I hope you learned a lot, took really good notes. This particular lesson did have a lot of information in it. So very good. Good work, and I'll catch you later.